Je voudrais remercier Filippo Vicentini d'avoir accepté de donner cette première séance, surtout après une journée déjà bien entamée. Et donc c'est un séminaire un peu particulier, il va être un petit peu plus long que les autres, je pense, où il y a d'une part une partie recherche sur les applications de ces méthodes sur les systèmes ouverts, et d'autre part aussi une introduction à NetKet, qui est cette bibliothèque de code dont j'ai parlé tout à l'heure et dont Filippo a été un des principaux développeurs. Donc pour vous dire quelques mots sur Filippo, il a fait sa thèse à l'Université Paris Diderot avec Cristiano Ciutti sur les systèmes dissipatifs, systèmes ouverts. Et puis, après un bref passage virtuel par New York, au moment du Covid, il est parti en postdoc à l'EPFL, où il travaille avec Giuseppe Carleo. Il a travaillé avec Giuseppe Carleo et d'autres à l'EPFL. Et depuis très peu de temps, il est revenu en France sur une chaire Monge à l'École polytechnique, chaire Monge qui est intitulée Matière condensée et intelligence artificielle. Voilà, donc en plein dans le sujet de ces cours. Et donc on est très content que Filippo ait accepté de venir donner ce séminaire. Je voudrais vous encourager, this I'm going to say in English as well, I would like to encourage you to ask questions during the talk, so to make it a little bit more lively. Okay, Filippo.
Thank you for the introduction, and thank you for the invitation. Well, the talk was already introduced, so I will jump right in. I would just like to start from saying a few words about essentially why I'm working with neural network quantum states, and especially what is the problem that we're trying to tackle, so that we can move on to more problems, in a sense. So, well, the main problem is the quantum many-body problem, that at least in the formulation that I'm interested in, means that when I try to study a system made up of many interacting quantum particles, in general, I will try to do that with a computer. And to store the wave function on this computer, I will encounter this exponential memory complexity, meaning that if I want to store the wave function, I will require an exponential amount of memory to store it, and therefore I can maybe store the wave function for 40 or 50 spins if I have a very big supercomputer, but eventually it's impossible. Another aspect of the many-body problem is a computational complexity problem. So this is slightly different in the sense that while the first one, it's about storing the state and representing the state, the second statement is about the cost of computing expectation values, which are, of course, fundamental to the study of quantum physics. And essentially, even if I can solve the first problem, so the memory complexity, and somehow compress the wave function to some very efficient data structure, I will still have to decompress it eventually to compute expectation values. And those expectation values will incur an exponential number of operations. And you've seen this morning how we can use those variational methods, and in particular neural networks, to approximate the wave function, which for me is simply this map that takes bit strings, so a sequence of n Boolean numbers, if we are discussing qubits or spins, and outputs a complex number. And the idea behind the neural network quantum state, as you have understood, is to approximate this function with some neural network functional. However, as I said before, this doesn't solve the computational problem. And to address it, we need to resort to Monte Carlo sampling, right? Meaning that instead of computing these sums over the whole Hilbert space, I can replace those with some classical expectation values over the square amplitude, over the Born probability amplitude encoded into my wave function or neural network. And I only need to compute some so-called local expectation value or local estimator, which for most physical observables and physical Hamiltonian can always be computed efficiently. So there are other variational ansatz, such as tensor networks, where essentially we don't need to resort to Monte Carlo sampling, because tensor networks essentially solve both those issues at once. In a sense, a tensor network can be contracted exactly with a polynomial number of operations. But for most variational ansatz, or at least for neural network quantum states, we need to resort to those two techniques. And of course, as you've seen this morning, we need in some way to find the parameters of this neural network that encode the state we're interested in. So either the ground state of some quantum Hamiltonians coming from some lattice models, continuous space ones, or from chemistry. We can study excited states using different techniques, or we can study the unitary dynamics. There is also another application that will be discussed, I think, in a few weeks by Juan Carrasquilla, which is using those neural network architecture to reconstruct some state, some wave function that is some samples generated from some quantum state using some quantum computer or over black box. However, all those applications that you see here, they focus on pure states and on, in a sense, unitary dynamics. And as I come from the field of quantum optics and let's say open quantum systems, what I would like to do is go beyond those and try to study some other problems, more complicated in a sense, such as investigating the finite temperature behavior of some Hamiltonians. Of course, this is relevant to know whether some phase transition is not washed away by thermal fluctuations. And this means I need to find some way to compute quantities or expectation values over some Gibbs states at a certain temperature. As I said before, I'm interested in the physics of open quantum systems, which essentially means I will couple my system, which has a certain Hamiltonian, with an environment, of which I'm not extremely interested in the microscopic details, so I will trace it away, but it will have some effect on the dynamics, and it gives rise to some new phenomena that is not present in the equilibrium models that we call dissipative phase transitions. And finally, there are many open questions about the systems and how they can be leveraged, for example, in conjunction with quantum chemistry or many other fields. The field of open systems is also relevant to quantum technology, since that any quantum computer or quantum simulator is an inherently open system, because we try to go to very long times, in a sense. We want to look, and therefore the approximation that we usually use to say that those systems are isolated can no longer be employed. And what is very important about this is that if we want to learn how to control and how to better leverage, let's say, the environment that acts on those systems, we need to have some ways to study those inherently many-body systems. And finally, the last, let's say, piece of the puzzle is to study the action of measurements on quantum systems. This is connected to open systems because you can always do some sort of unraveling of the master equation or of the open dynamics onto a set of trajectories where the environment is in a sense measuring my system. But it's also interesting because it's connected to some very new field that is emerging very rapidly, known as measurement-induced phase transitions. So, in a sense, the first part of this seminar is about finding a way to discuss and to tackle these three problems. And later, as Antoine said, I will discuss NetKet. So I will start with what is my target. My target is to describe mixed states, essentially density matrices. And this means that I need to enforce, in general, three conditions, right? One is the Hermitianity of this object. One is the fact that it must have, it must be semi-positive definite, in the sense its spectrum must be larger than 0, of course, because it's encoding some classical ensemble of quantum states. And in principle, we would also want to ensure that it has trace 1, but in practice, pretty much like neural quantum states are not normalized, we will not worry about this requirement. As far as I know, in the literature, there exist three possible approaches to encode mixed states with neural networks. One, maybe the most straightforward, is to simply expand my density matrix onto a set of pure states. Essentially, I just take a few pure states. There was psi, which of course should be polynomially many, such that this approach is efficient, or let's say is manageable. And then I can slap in front of them some probability. And this object is automatically physical, in a sense, because I've taken a superposition of a few different pure states. And I can use neural network quantum state to encode every single one of those pure states. So if I want to take a density matrix of rank 5, for example, I will take 5 neural quantum states. However, this is expensive if I want to go to high temperature or very highly entropic quantum states, because, of course, the cost grows linearly with the rank of a density matrix. And so this becomes very quickly very expensive. But it's very effective to study finite temperature physics. The second approach is to, in a sense, generalize what was shown this morning to a matrix. So instead of encoding the wave function, or better yet, the logarithm of a wave function, onto a function that takes as input these bit strings, this sequence of Boolean numbers that essentially label all the entries of my wave function, I make now my neural network take 2 inputs, one labeling the rows and one labeling the columns of my density matrix, and then I approximate this with a neural network. This has been used widely for open quantum systems, for tomography, and to simulate both the dynamics and the steady state of these kind of systems. However, the problem is that depending on the neural network architecture that I choose, I will be able or not to enforce some properties in this, some physical properties in this density matrix. The last approach, it's the one is in spirit very similar to this one. Essentially, the idea is to expand the density matrix not onto a basis of a standard complete basis of a Hilbert space, but onto another complete basis, the positive operator valued measurement basis. In a sense, what we do with this encoding is that if I have a single spin or qubit, for example, I can take a local basis of dimension 6. So I can take all the possible outcomes of the x, y, and z measurements. Essentially, I can take the distance between the origin of the Bloch sphere and every point along those axes. Now, this is another complete basis. So, of course, it doesn't enforce physicality. It doesn't enforce necessarily positive definiteness. And it can encode some results which are completely unphysical. It was originally proposed by Juan Carrasquilla in the context of quantum state reconstruction or quantum state tomography, and it's also later been used to study open quantum systems. So the first application I would like to discuss is in the context of finite temperature calculations. And I will try to stay away from encoding density matrices with neural quantum states because it's, in general, very hard. So the idea is I want to compute some thermal expectation values over this object. And you know very well that I can unpack, let's say, the Gibbs state into this structure. Essentially, I split the exponential into 2 contributions and insert an identity in the middle. And now this object is a pure state. So if I had an algorithm to compute this object, to reconstruct this object and compress it into a neural network quantum state for every single sigma, then I could actually try to study very large many-body quantum systems at a finite temperature. And there is an approach. So if you want, this idea is also arose actually in the field of tensor networks. And what some researchers recently did was to generalize it to the field of neural quantum states. And the idea is relatively simple. We want to initialize a neural quantum state to this sigma configuration, to this basis state. And to do that, we solve an optimization problem and essentially we fit our neural quantum state, which has some parameters theta, to this basis element. By solving this optimization problem, I will find a set of parameters such that my neural quantum state approximately encodes this basis state. And the way we do that is, of course, by using some stochastic estimator for the loss function, because otherwise we would have to compute exponentially larger like expectation values, and we would have an exponential high cost. So what we do is we sample my neural quantum state at every step for a certain set of parameters theta. I check, this should be an eta actually that is sampled. I look at the distance between psi of theta, so between my neural network quantum state and my target state, and I try to optimize this quantity.
Excuse me.
Yes?
To understand, why do we want to minimize this distance?
So if you want, I want to write a neural network, okay? I want to find the parameters of a neural network that encodes a basis state, a sigma, okay? The best way is to just fit, if you want, my wave function encoded into the neural network to the wave function amplitudes. Does it make sense?
Not yet, but we are on the same level.
So if you want, what I'm trying to do is to have a two-step algorithm. First, I'm trying to, my target is to reconstruct this psi theta of beta, okay, this object. So the way I will do that is to first find a neural quantum state encoding for this state, and then to perform the imaginary time evolution using e to the minus beta half h. That's actually the next step. So the second step is to simulate the imaginary time dynamics. I will not say much about this because it's the discussion, it's the topic of the next seminar, of the seminar next week by Giuseppe Carleo. But the idea is that, very roughly, I will look at a way to update my parameters. So a small change of parameters delta theta such that my network with the updated parameters approximates the state to which I apply the identity minus delta beta h, meaning the linearized imaginary time evolution for a very small imaginary time step.
Filippo, perhaps in the same vein as the first question, am I correct that there is a trivial solution, at least to the first problem, which is, imagine I put all the connection between the visible and hidden. Imagine I use an RBM, I put all the connections.
Yes.
I put the fields, the local bias, as I want, to favor a spin up or spin down when I want it to use the sigma state. That's a solution.
Yes, so there are two problems with this approach. First, it only works for example, for an RBM, or if you have a visible bias. If you have some more complicated neural network architecture, it might not be trivial, the way to find this solution. And second, this kind of solution, again, I would have to discuss something that I don't really want to discuss, but they work very bad. They are very bad starting states for these imaginary time dynamics, and therefore we try to avoid doing this. And in
So you are saying that other parameter configurations, different from the one I mentioned,
yes,
which seems very singular indeed,
yes.
which is much better for the
If you want an intuitive explanation of this, is that you have, imagine you have your parameter space, okay? You have sensible parametrization, which live in a, let's say, in a sphere around the origin, and the parametrization you're looking at, the ones we know how to write analytically, are very far from them. They are some singular. And so, while if we find the parametrization in the bulk, then we can also do the dynamics, which is somewhat continuous. But if we look at those singular parametrization, it will be very hard to go back to the bulk. And those, let's say, dynamics algorithms are not able to actually study the dynamics of those configurations. So if you want a way to find those typical thermal states at some beta temperature, is to first fit my initial configuration. It can be a single, let's say, bit string like sigma. It can be something more complicated. And then I will use the imaginary time dynamics to evolve it up to a certain to a certain temperature. And essentially, it's possible to show that this problem can be linearized in delta theta, and this yields this kind of differential equation for the parameters. Again, I will not say much about it, but you can think that I can remap the Schrödinger equation of motion, which is a differential equation for the wave function, onto a differential equation for my parameters, which approximates the imaginary time Schrödinger equation. Is that clear? Okay. So once I have an algorithm to compute for every configuration sigma the typical state at a certain temperature beta, then I can find a way to compute expectation values at a finite temperature. Essentially, I take the definition of expectation values over a mixed state, and I replace this definition of my Gibbs state inside of it. And then, if you recall, this morning you've seen that to compute expectation values over a pure state, I also need to take care of a normalization, because neural quantum states are usually not normalized. So the last term in this equation can be obtained with all the algorithms that were discussed this morning. And all I need to do is to keep track of, or some way to estimate the norm of my neural quantum state at a certain temperature. And if you recall what Professor Georges said this morning, is exactly that we cannot do that. We cannot estimate the amplitude of a neural network quantum state, because it would involve the sum of the whole Hilbert space. So we go back to the problem of exponential complexity. However, thanks to some properties of the unitary time, of the imaginary time dynamics, it's possible to show that the norm of the state respects a differential equation and essentially evolves according to the energy. And therefore, if we are able to know the norm at the initial state, which we know because we fitted it to a state with norm 1, then we can, if we keep track of how the energy varies along the imaginary time dynamics, I can essentially reconstruct what the norm is at any finite temperature. So the overall algorithm is the following. I sample a set of configurations sigma. I fit a neural quantum state to this configuration, and then I evolve it in imaginary time, and then I keep track of the energy along the evolution to essentially reconstruct this term, and finally I average across all those trajectories. Again, this algorithm is also used in the context of tensor networks. And this very nice paper by Henry and co-workers, which came out last year, they've shown how that this approach can be used to study the Heisenberg model in 2 dimensions, for example, for a 6x6 and 8x8 lattice. And they found somewhat good agreement at the relatively high temperature, but then the agreement starts to diverge somewhat at low temperature. Moreover, there is one problem that they don't really discuss, but shows up, is in the way we initialize the neural network quantum state. Essentially, to set up the neural network to reproduce this very peaked state, it's not an easy task, and many researchers have had problems in this, and therefore, instead of using the sigma z basis for those initial states, we use some more complicated ones. When you see this discrepancy at low temperature, that's probably due to the fact that they're using very few hidden units. So if you see, they have as many hidden units as number of spins. So that's very small, essentially. And probably those states are not able to reconstruct the ground state of the system. And the last problem of this approach is that it has a very high computational cost. Essentially, for those plots, there are up to 100 trajectories. And therefore, I need to repeat the same full dynamics 100 times, which is somewhat expensive. So there is another approach, also coming from the field of tensor networks, known as thermofield dynamics, where essentially we start from, we try to go a bit more closer to the density matrix, and we try to ask ourselves the question, how can we construct a density matrix? And there is one approach, which is known as the purification ansatz. Essentially, you take a wave function in a larger space. So in your physical Hilbert space tensor, some ancilla, which you will want to take as large as the original state, and then you trace over the ancilla. And this will yield you a physical density matrix. Now, you can assume, for example, that I know how to write the infinite temperature state, the state in this system tensor ancilla where if I trace away the ancilla, I get the infinite temperature state. And this state, in general, has somewhat this structure of a locally purified density operator. Essentially, you have these kind of entangled states between every physical spin and its ancilla. And so when you trace away the ancilla, you get somewhat the identity locally. So now the question is, how can I go from this state that I know how to write, that I know how to write its purification, to any temperature? So the most trivial way to do that would simply be to perform the imaginary time evolution, right? To apply this e to the minus beta over 2 times h operator to the left and to the right. And now I can also bring it inside the trace, right? And then, of course, since this operator, the Hamiltonian, is acting only on the physical degrees of freedom, you can think that I have to add some tensor identity that acts on the ancilla. But now, those two states are the same, right? So instead of evolving the full density matrix, I can start from this infinite temperature state that I somewhat know how to write down analytically, or I can prepare with the same fitting algorithm that I discussed before. And then I can perform this imaginary time dynamics, where I'm only acting with my Hamiltonian on the physical degrees of freedom, and I'm acting with identity on the other ones. This approach was first generalized to neural network quantum state by Yusuke Nomura and collaborators in 2021. He framed it slightly different, but essentially this is the message of what he was doing. And once you do this, you can always compute the thermal expectation values as standard expectation values over any pure state. So they benchmarked it on a few models, in particular on the J1, J2 model in 2 dimensions. So they scanned very different, like somewhat wide range of temperatures, and they found extremely good agreement with exact solutions that I think they computed using quantum Monte Carlo. So this approach, in my opinion, is, as of today, the best approach to study finite temperature physics using neural quantum states, because you only need to do one trajectory, one pure state trajectory, but for a much larger system, for a wave function over a doubled system size. And for a while, we wondered, can we use this same approach to study open quantum systems? But unfortunately, this trick, so essentially the fact that we can act to the left and to the right of the density matrix independently, and so that we can just evolve this purification, is specific to finite temperature calculations and doesn't generalize to, for example, the Lindblad master equation. So just to recap very, very quickly, very briefly what I've said until now, essentially, as of today, as far as I know, there are 2 approaches to studying the finite temperature physics with neural network quantum state. One is using those typical thermal states, which is very straightforward, but can be relatively expensive because you have to run many trajectories. And so especially at high temperature, this might give you somewhat higher cost. It's possible to refine it somewhat, but that's the idea. We can use this thermofield, where you only evolve one trajectory. But in the end, the main problem of those approaches is that simulating the dynamics, in a sense, when we initialize the state, we have this very peaked state. If you want, I have somewhat of a delta, a Dirac delta in my Hilbert space, and then I want to evolve this state. And in the seminar next week, you will see why this is a very hard problem. So with that, I would like to move on to studying, for example, open quantum systems, which is actually how I got into this field a few years ago. So the idea here is that I will focus only on Markovian open quantum systems, so those that are described by the Lindblad master equation. Essentially, if you want, this is a master equation for the density matrix, where I have one coherent evolution term that essentially encodes the Heisenberg equation of motion that everyone knows, plus another term which encodes the incoherent evolution due to the interaction with the environment. And essentially those L operators here are what we call the jump operators, or the operators that encode how the environment affects the system. So for example, if one dissipation channel is a de-excitation, it might be a sigma minus. If I have decoherence, it might be a sigma z, and so on and so forth. And pretty much like in pure unitary dynamics and let's say in the world of pure states, you are interested in the ground state of an Hamiltonian. When we study the Lindblad-Master equation, we are often interested in studying the long-time dynamics, so the steady states. And under relatively reasonable assumptions, we know that a steady state always exists. So there are two ways to approach this equation. One is to study it at the level of a density matrix. Essentially, I can try to solve this problem, right? L applied to rho. L is my super operator that encodes the master equation. L times rho equal to 0 means that I'm looking for the steady state. So for the state rho that doesn't evolve anymore. I could also simulate the dynamics in real time until I converge to the steady state. This is somewhat similar to how you do some imaginary time evolution to converge to your ground state in pure systems, but here we have an attractive dynamics in real time. And another approach is to essentially unravel the master equation onto a set of individual trajectories where we don't only have the Hamiltonian dynamics, the unitary dynamics, but we also have some jumps. Some terms that are stochastic and that essentially encode the action of the environment on my system. And I will not discuss this second approach because, again, there is this issue. When I apply a jump operator on my wave function, I set to 0 half of my wave function. And as you will find out next week, it is very hard to study the dynamics of this kind of problems, which essentially means that nobody has yet managed to really simulate quantum trajectories with neural network quantum states as of now. I mean, we're working on it. So this is what I would like to discuss today. It's how to target the density matrix. So if we are looking for the steady state, what we can do is we can simply look for the density matrix rho for which we have L rho equal to 0. And so we can use this as a variational principle. I can construct, if you want, this object, this trace of rho dagger, L rho. This is a positive number. It's, if you want, a square value. And it's possible to show that this is exactly equal to 0 only when you have found your steady state. And so pretty much like you would try to minimize the energy in some ground state calculation, here we try to minimize this L dagger L quantity. If you want, in a sense, what we are doing is that we are taking our density matrix, we are vectorizing it, so we get some wave function in a doubled space. And then we try to find the ground state of an Hamiltonian, which is L dagger L, which is now Hermitian. There is another approach, which was first used by Alexandra Naghi and Vincenzo Savona, and by Giuseppe Carleo and Michael Hartmann, when we came out all together in 2019 with a few works on this problem. And the idea here is to simulate the dynamics encoded into the Lindblad-Master equation. As I said before, we can remap the dynamics of the wave function, but also for the density matrix, onto a differential equation for my parameters. I will not get in the details of why it has this particular form, but it's related to the natural gradient and the so-called time-dependent variational principle. And then essentially what you would do in this case is to integrate your equations, this differential equation, until you get to sufficiently long time such that you reached the steady state. At first, a few years ago, when we were discussing those ideas with Cristiano here, we were thinking about using this approach, but essentially we decided to avoid it because in a sense, when we wanted to study phase transitions, where we have some critical slowing down of the dynamics, and therefore it might be very hard to find the steady state using those techniques. We will have also the same problem in this case, but we were hoping to avoid them. So in a sense, what I've showed you now is what is the cost function that we are trying to optimize to find the steady state. Let's say it's this one, right? But I haven't told you anything about how to encode the density matrix, because I tried to put off this, tackling this problem until now, because I was trying to say, look, we can do finite temperature with pure quantum states. So I will finally get to this and how we can encode density operators with neural network quantum states. So the idea is the same as you've seen this morning. Instead of having one set of n Boolean values, so that they can label the 2 to the power of n elements in the Hilbert space, we have two sets of such variables, one that labels the rows and one that labels the columns of my density matrix. So in a sense, my neural network architecture will take as input 2n Boolean variables, and it will output a complex number. And now my question is, can I make sure that the output of the neural network respects the physicality conditions? So it's Hermitian, it's positive definite, and well, I will not consider the trace one. So the most simple approach I can take is to simply use the same architecture that was introduced this morning, so essentially a restricted Boltzmann machine or a one-layer neural network. I have the notation here is a bit wrong, so the sigma tilde would be the eta. Essentially, I have a block of those, I have those n variables for the rows, those n variables for the columns. I multiply them by some matrices that can be real or complex. I apply some nonlinear activation function g, and then I sum over the output. Of course, this is exactly equivalent to what you've seen this morning. So this is encoding no structure at all on the density matrix. Essentially, I'm parameterizing a vector in this vector space of doubled size. Encoding Hermitianity, however, is extremely simple. You simply need to make sure that if you swap the rows and the columns, you get the complex conjugate. So what you can do is you simply, assuming you are complex, actually, you can take those u to be u1 and u2 to be the same, and then 1 is the complex conjugate of the other. And you will want to take, if you have some bias term here, this to be real. And in this case, this function, if you swap the rows and the columns, will give you the complex conjugate, and therefore you have something that is positive definite. Sorry, you have something that is Hermitian. But we still want to encode the positive definiteness. In 2018, Giacomo Torlai, which at the time was doing a PhD at Perimeter Institute, I think, he noticed that if he was thinking, again, about the purification ansatz, and if we could use this idea of purifying some very simple neural network to get an exact description such that the density matrix was positive definite. Essentially, there are two problems with the purification ansatz. So if you have, you can encode some pure state with the ancilla, but if you want to perform the full summation over the ancilla, well, this is exponentially costly, unless you can sample it, but sampling the configurations of the ancilla doesn't necessarily work. I mean, it works for pure states because of a particular structure of what we are doing, but will not work in general. However, if you take a very simple or very shallow ancilla configuration, meaning if you take your wave function in this Hilbert tensor ancilla space to be something that only depends on your physical degrees of freedom, this gamma, times this, if you want, exponential of the configuration of your ancilla interacting with the physical degrees of freedom. If you want, in a sense, this is literally a restricted Boltzmann machine where the ancilla are your hidden degrees of freedom. Then you can trace away the ancilla analytically, because, I mean, this is a very simple mathematical problem. Essentially, you substitute this expression into the purification ansatz, and you will get a condition on the nonlinearity. So the message is, if you take a very shallow ancilla for an RBM on the physical tensor ancilla space, you can purify the ancilla analytically and get a condition on the nonlinearity. And for example, you will find that if you take log cosh, this satisfies the constraint. So So if we take this structure as a neural density matrix, if you want, we have two terms that encode some pure state or some pure component in my state, and then I have another term that encodes the mixedness. Then, assuming I have a good activation function, this gives me not only an Hermitian but also a positive definite operator. The problem is that this approach only works if I have a very shallow ancilla, so an ancilla of this structure. And so, in a sense, this means that the interaction between the sigmas and the etas, so the mixedness in my system can only be encoded with a single layer, which is, if you want, the mixing part of my neural network can only be one layer deep, which is not very good because we know that we want to make neural networks very deep because the expressive power increases with the depth. So a few years ago, I started asking myself the question if we could make a deeper ansatz that is also pure. And essentially, together with Riccardo Rossi, we identified two ingredients that we could put together. One is what we call the gram matrix. Essentially, is the purification of a small ancilla. If you take an arbitrary neural network, which depends on some physical degree of freedom and a small ancilla, where the ancilla can take over very few values. So for example, it's a bosonic ancilla with two possible configurations, one or two. Then you can numerically sum over all those configurations, even if you cannot do it analytically. And you can construct this density matrix, which has a very small rank D. And then we use the second ingredient, which is the Hadamard product. So I will not prove it, but if you take the if you take the Hadamard product, which essentially means the element-wise product of two positive definite matrices, then you also get a matrix that is positive definite, and its rank is bounded exponentially. So if I put together those two ingredients, so if I take a polynomial number of density matrices with a very small rank, and I take the element-wise product between them, then I can construct some state that is in principle, that encodes in principle an arbitrary amount of, entanglement, depending on those psi I, and also of entropy. And it's interesting because in a recent paper we discussed how essentially this architecture is related to a set of entangled placket states that span the whole system, and we are taking many overlapping plackets. Every placket has a relatively small entropy or small rank, but if you overlap them, so if you take the product of all those states, you can construct states with very high entropy. And I will later show how using those two tricks allowed us to actually improve on the previous architecture. So here I said nothing about the neural network architecture, yes, or this psi I, this object here, because I want to keep it very, very open. Essentially, you can plug in here any neural network architecture you want. This is just some high-level structure to describe this object. And and then it's also possible to further refine this model to allow for autoregressive sampling and some other properties, but I will skip that. So to finish, I would like to show you a few of the results we had with those techniques, in particular on the driven dissipative transverse field-Ising model. So this is a very simple model where, the transverse field-Ising Hamiltonian, I think everybody knows it, and then we are adding this dissipative term. Essentially, every once in a while, the environment de-excites one spins from the up configuration to the down configurations. So this was our work from 2019. Essentially, by minimizing this loss function here, we were able to show that if you perform any optimization, you are able to reduce, let's say, this LDAG-RL loss to relatively small values. And as we reduce this quantity, of course, we also found that the observables, such as the magnetization along sigma x, converges towards some exact value. And those calculations were done with the first shallow purified ansatz by Giacomo Torlai. Moreover, we found that even if there is a small error sometimes, we could improve on the error by essentially increasing the width of my neural network, which is very important for this kind of variational calculations because we want to be able to improve our results by increasing the size of a neural network. And eventually, we tried to study to scan the full transverse field intensity for this model. And we found that when we had a state that was somewhat like close to very low driving, so the state was essentially something very, very pure, then we had very good agreement with the exact calculations. We had very good agreements at very high field strength, so when the entropy is very high, but in the intermediate region, we had somewhat bad agreement. A few years later, so actually last year, we tried to redo those same calculations using this Gram-Hadamard encoding coupled with a deep neural network. And we were able to show that actually, by using those deep ansatz, we were able to converge to much higher accuracy. And now I will not get into the details of it, but using those deep architectures, we're also able to study quantities such as the Renichoux entropy or the purity of the state, which allows us to query more properties of those systems. This very same model has been taken for reasons I didn't really understand as a benchmark by the community. And it was also studied by Di Luo at MIT and collaborators. We tried to use this positive operator valued measurement basis to encode the density matrix. If you want, as I said before, those A's essentially run over all the possible outcomes of some set of measurements. And since this is the probability to find some measurement outcome, then the neural network you need will only output a probability distribution. And by minimizing some related loss function, they were also able to find somewhat good agreement. Now the orange is the result, good agreement to the exact data and improving on the original results we had. Finally, I will just flash very briefly, as I said at the beginning, when we started looking into open systems with neural networks, some groups also were looking at performing the dynamics. This will be discussed more in depth by Giuseppe Carleo next week, but eventually the idea is that you can integrate this differential equation for the parameters and study, in this case, the XYZ model. And this is the paper by Alexandra Nagy and Vincenzo Savona back from 2019, where they were able to find very good agreement with the exact data, at least for the spin structure factor of this model for 2x2, 3x3, and then 4x4 they could not benchmark it at the time. By now we know that this architecture was a bit off, but this particular problem has not been investigated again using these architectures. And this same problem was with the transverse field was also studied by Moritz Reh and Markus Schmidt by using the POVM ansatz, which instead allowed us to get a much better result. I will skip the last part on the trajectories. I will skip roughly to some conclusions before I move on to the next part. So the message that I would like to pass to you is that if you want to study finite temperature states, we already have a set of tools that works quite reliably. We still have some problems with performing the imaginary time evolution, but those are not unsurmountable. And even if there are few works on the subjects, I think this is a domain where more workforce would be welcome, more people investigating those problems would be welcome. For mixed states, essentially encoding positivity of a matrix is very hard. I've shown you that we can either use those very shallow shallow ancilla purified ansatses proposed originally by Giacomo Torlai, but they have some issues in the sense they cannot represent any state. At least we were not able to use them to represent any state. I've shown you some recent generalizations and a mapping to entangled plaquette states, and a question that is still open in the field is a comparison between those two approaches. So essentially whether the POVM ansatz and the POVM encoding of a density matrix is better or worse than those neural network encodings over the sigma z basis. Some of the open problems in the field of open quantum systems mainly is still that of applying measurements and performing, if you want, quantum trajectories with neural quantum states. We are working on it. I think that some results will be presented next week, but there are still several questions about how to effectively perform this kind of evolution. And again, the problems essentially arise every time you want to describe a structure that has many zeros, such as a state after a measurement or a density matrix, which has many zeros. And we are still investigating how best to avoid these kind of problems. So with this, I will quickly thank some of the collaborators, so Alberto Biella and Cristiano Ciuti, that, with whom I first got into this field, and some of the people from EPFL and Sorbonne with whom I worked on those topics. And I will, particularly Giuseppe Carleo, and I would like now to move on to give a brief overview, very quick overview of NetKet, which is the software that we have developed to essentially study and use neural network quantum states in practice. So I think if there are some questions on this first part, I will take them now, maybe.
Maybe I can ask one.
Yes?
So at some point you mentioned the time-dependent variational principle for the dynamics of this open system.
Yes.
Can you say, yeah, so which variational principle I should think of it? Because it's not the Dirac variational.
Okay, so here we get, okay, so this is a bit technical. There are three variational principles, right? You have the McLachlan, the Dirac, and the time-dependent variational principle itself. Essentially, the idea is you can, when you go from the variational manifold to the if you want, when you go from the tangent space of a variational manifold, so the space where this delta theta or delta v lives, the update of your parameters, and you try to project it somehow onto the tangent space of your Hilbert space, then you can discard some information, and depending on what information you discard, you get one variational principle or the other. For
I guess more physically, like you don't minimize the energy because the system is open.
Yes.
You don't conserve the energy because the system is open. So what are you doing when you choose this? Is there a way to understand what physical principle you are enforcing in choosing?
Physical principle, I would say none for open systems. We are simply, so from a differential geometry point of view, I'm applying L to rho in the, so I'm taking a vector from the tangent space of the Hilbert space, which tells me how I'm moving across this manifold, along the Hilbert space. And then I do the pullback and I try to find how this object maps onto my variational space. I'm not enforcing anything else. If you want, there are problems in doing the dynamics. There are issues because we have to choose a certain distance function, as Antoine said this morning, to construct the quantum geometric tensor, which I didn't specify, but it's actually this S matrix. You have to choose some distance metric between two objects. For wave functions, it's very easy. You take the Hilbert-Schmidt norm, what is induced by the Hilbert-Schmidt norm. But for open quantum systems and mixed states, you have an infinity of possible distances to pick from. But there is only one that we know how to compute efficiently, which is the L2 norm, the vector norm. But the vector norm is not really physical for mixed states, right? We would like something more like a trace norm, spectral norm, these kind of things, but we cannot really use them because we would need to diagonalize the density matrix. But in the first place, we don't want to do this kind of global operations that require us to query every entry of a density matrix. So I would say it's still an open problem.
So Filippo, the open problem you mentioned is to find physically meaningful definition of the metric tensor on density matrix space.
Yes.
Which is at the same time computationally feasible.
Exactly. So there are.
S is my G, right?
Yes, S is your G, exactly. So the only way that you can find a quantity that you can efficiently sample from and compute is to choose as the distance, I mean, the vector norm, the L2 norm, right, between two states. Because why we want the L2? Because the L2 is local in the basis. So I can compute the L2 distances between psi of sigma and psi of theta, or two states, and looking only at a small number of samples. Instead, if I wanted to look, for example, at the distance between a small number of eigenvalues of rho, I would still need to diagonalize the full matrix, and so have access to the full matrix. I mean, modulo all those randomized linear algebra techniques, which I think is very interesting, but nobody ever tried in this context. There is, I will remark, there is a paper, mostly incomprehensible, unfortunately, by Google people and a guy called Faris Esbahi, who now left Google to found his own startup, who proposes a different distance matrix for mixed states, but I'm still trying to decode the paper. So, Faris, F-A-H-R-I-S, Sbahi. S-B-A-H-I. The paper is typical Google style, 70 pages long. It's very interesting, but so they try to use something on the diagonal of the density matrix. I think it will only work for when we couple, let's say, if we do something like that. I will get there. Yes. So if you use this encoding onto a set of pure states, you could also encode the P onto some neural network, and the psi, they could be the output of a quantum circuit. Like you apply a unitary gate onto some basis set, and I think that's the problem they were targeting. And in that case, you can find a very relevant metric, but if you don't do this assumption, it doesn't really work.
Excuse me.
Yes?
A quick question on this slide that I was not following, so this will be a naive question, but why does the Pauli Z basis not, why does it depend on the neural network architecture compared to the other approaches?
So, imagine you have a neural network, a black box that you put in some parameters, okay, and it shoots out vectors in the Hilbert space. If you put in completely random parameters, the output will always be a valid vector in the Hilbert space, right? Because any vector in a vector space is a valid quantum state. Maybe very exotic, maybe it doesn't respect symmetries, but it's always a valid quantum state. Now, for density matrices, this is not the case. If you take a random vector, then you reshape it into a matrix, in a sense, most likely the spectrum of this matrix will not be positive. Okay? So that's what I'm saying. While this encoding, you're just summing over some pure states, essentially, and therefore this is always Hermitian and positive definite. To enforce Hermitianity and positive definiteness in this architecture, you need to take care and discuss the details of a neural network. And this also means that you have to constrain your architecture. And very often when we constrain the architecture, we are doing a trade-off. We are enforcing something like symmetries, or we're getting exact sampling with autoregressive properties or something else, but we are giving up something else in exchange, usually representation power. The neural network architecture will be less effective to encode arbitrary states. It's hard to make an exact statement, but it's something we see in general. And which is why at some point, like Juan Carrasquilla and Marcus Schmidt, they started looking into this POVM basis, because in this case, if you want, you are unconstraining the neural network even more. You're saying, just output anything, I will accept it. Maybe it's not physical, but I don't care. So this encoding is completely unphysical. So if you put in arbitrary parameters on this probability distribution, you don't have a positive definite quantum state. Actually, you have noise, essentially. But, OK, there is some physical structure to it. But essentially, they found that this allowed them to use some neural networks that work very well. It's very empirical, let's say. One of my projects right now with a master student is to try to essentially study the connection between those two families, essentially in the context of tomography. But I mean, there is not the time to discuss it today. And yes?
So regarding can we see in the plots you made the unphysical nature of the code? Is it the noise you see, or?
No, you cannot. So one way to see it is this. So here, with a physical encoding, I can minimize this loss function. Okay. No, sorry, this is still fine. No, you cannot see it from here. Actually, I will say. The way it shows up usually is not in the quantity we minimize, because when we minimize something, we get it very good. But it's in what you don't minimize. So unfortunately, nobody reports correlation functions. I think even Marcus Schmidt doesn't. No, those are correlators. So in general, where you see this unphysicality is when you start to look at very pure states. So if you look at very mixed states, the probability distribution used in these POVM ansatz is essentially flat, because if you want an infinite temperature state, you have the same probability to measure to get pretty much any outcome. But at 0 temperature, you have a lot of constraints, right? Because the fact that your state is a quantum state, that you just are taking this object, which is psi, gives you a lot of constraints on what you can measure on it. Essentially, you don't want to violate Heisenberg inequality principle and a few other things. And so the probability distribution starts to have a very well-defined structure. So what I've seen in some calculations in practice is that if you try to use the POVM ansatz to study some very pure state, it doesn't work as well as when you try to study some very mixed state. But beyond that, I think there is very little. It's very little studied and understood how the two approaches, let's say, how the two approaches perform. There is a very practical problem, if you want, is that we have an implementation of the first approach, and they have an implementation of the POVM approach, and both groups never had both implementations. So nobody ever benchmarked both. Yes?
You mentioned that you impose some restrictions related to the symmetry to the neural network. Is this done before the deep learning phase, or we restrict the parameter space, or we restore the symmetries after exploring the whole parameter space?
You can do both. Again, the most simple thing to do would be to, in this encoding, right, you take individual wave functions or neural networks which are symmetric under some lattice symmetries, for example, and you sum over those. In those approaches that operate on the let's say, on the full density matrix, you will want to enforce lattice symmetries by acting on both the rows and column degrees of freedom. At the same time, there is a procedure. It's fairly straightforward, but nobody has ever published any work on it in practice. I don't know why, frankly. But in general, what you do is you can enforce symmetries at the level of a neural network, which usually means at the first layer. So in connecting to what was shown this morning, it's possible to easily make those architectures invariant under some symmetry operation. It's still unclear how to make them equivariant. It's surely possible, but nobody has investigated that. Okay, so if there are no more questions, I would like to show off a few things, especially for the younger ones that want to try to run some simulations themselves. The idea of NetKet, if you want, is to give you some easy way to access many of the concepts that were discussed today. So in particular, computing expectation values with Monte Carlo sampling, getting their gradients, computing the quantum geometric tensor, and running optimizations for the ground state or open quantum systems, etc. The idea is that, in general, most people will just want to write down their neural network architecture, or not even use one that is already done by someone, and plug it in a set of routines that are already written, optimized, and perform somewhat well. And that's why we want to use automatic differentiation, right? So it was this set of tools that allow us to get immediately and automatically the gradient of those neural network architectures and plug them in some algorithms. And that's why we use JAX, which is a framework by Google, a bit like TensorFlow and PyTorch, that allows us to do that. We chose JAX because a few years back it was the best choice for what we were trying to do. But of course, you could implement yourself all those algorithms in also PyTorch, for example, or other languages. So the idea of, so if you want to do a variational Monte Carlo calculation in practice, what you will need to do is you will need to write your neural network representation for the log wave function. Let's assume pure states for a moment. Then you will need to compute the formula for the gradient, right? Then you will need to write a Monte Carlo sampler. Then you will need to find a way to represent the Hamiltonian. You will need to find a way to compute the local energies, maybe estimate the errors, check if your Monte Carlo sampling is converged. And then you will want to write some optimizer to optimize the energy and loop this over. And then maybe you want it to run on the GPUs, so it's faster. You want to change the neural network and the gradients, and you don't want to rewrite everything in turn. And then you want to make it fast. So the idea is that those first two steps, essentially the neural network and the gradients, will be handled by JAX and any neural network framework written on top of it. We like Flux, but there are many others. And NetKet will sit here at the middle. Essentially, it will give you Monte Carlo samplers, a way to represent the Hamiltonians, and some algorithms to compute the local energies and estimate the errors. And then you can use other JAX-based packages to do the optimization and everything else. So the bottom line is, if you don't like, NetKet is both a set of individual tools, so some samplers, very well written, some Hamiltonians that can be written in such a way that we can scale to 1,000 of spins, essentially. And you can use them individually, but you can also use those tools. But you can also use those tools all together with some high-level drivers that essentially do everything for you. And I would invite every one of you, after this very short introduction, to essentially go on our website, like netket.org, where we have somewhat extensive documentation. It's not extensive enough, I know. I would love this if some other users started to contribute more documentation to it, but we have many tutorials, like the one I will flash today, and a few others. And so you can literally start playing with those. And you can run those on the cloud on a GPU yourself. You just press on this small button. It will launch a Google instance in the cloud that allows you to run all those notebooks on a GPU for free if you have a Google account. If you don't, well, that's a problem. And yes, so let me start very quickly. How can I do that? Let me duplicate my screen. Is this big enough? Yeah. Okay. Okay, so So for this short tutorial, let's say, I will consider a very single problem, that of computing the ground state of a transverse field Ising model, right? So, I mean, I think everybody in this room knows this is a Hamiltonian. So we have some transverse field acting along the x direction and on every side. And then we have some coupling along the z direction between nearest neighbor. And I will consider only a 1D chain. So skipping, let's say, the first things. So the fundamental object so first we usually import NetKet as NetKet, NK, but okay, that's very minor. The fundamental idea in NetKet is that we want to define like some computational basis we work in. So you've seen many times today that the input to our neural networks is this string of Boolean values, right? +1 or -1 or zeros and ones. And that's what we encode in an object that we call the Hilbert space. So for example, for spins, this means that we have essentially that we can query all the configurations, which essentially are all the 2 to the power n, in this case 20 configurations of O -1, O -1 except the last one, which is 1, etc., until the last configuration where it's all ones. So this object essentially is our way to declare what is the computational basis we're using. We could also use some other configurations like a qubit. So in this case, we would have in this case, we would have a basis where instead of using -1 and ones, we have zeros and ones. While this might seem a very simple and let's say, silly difference in practice, sometimes it can be very important to use this like something that is symmetric or not. So we allow users essentially to pick anything. And yeah, and essentially we can always query, I don't know, a set of random states. Sometimes it's useful from the Hilbert space. So essentially we can query some random configuration, some random basis elements from the Hilbert space. So in this case, I ask for 3 of those, and I get 3 of them. Now, the interesting point is how we build essentially operators. Okay, so in this case, I'm importing a set of operators from this netket.operator.spin module, where we have sigma x, sigma y, sigma z, and the identity, I think. And we allow users to combine them pretty much like you would combine them when you write an equation. So if I want to write down the sigma x operator acting on the first spin, I would write sigma x, open parentheses, hi. So Hilbert, you have to specify what is the Hilbert space. Essentially, this tells you implicitly how many spins we are considering. And you can specify, for example, you want it to act on the first spin, on the second spin, and so on. And you can also manipulate them. You can multiply them by some constant, and you can sum them together. And you can also multiply them together, and you can pretty much do anything you would like on them. Okay? So to write down the Hamiltonian for the transverse field Ising model, essentially what we do is first we write the transverse field term, so the sigma x term on every side. So here I have some list looping over the whole range of numbers from 0 to 19, and I multiply this by gamma, and then I sum them. And if you look at this object, so this, the resulting operator is called the local operator. The local means that it acts on a small subset, that the support of this operator is bounded and relatively small. So if you want to try to write operators that act at the same time on 10 spins or 12 spins, this will never work, because the encoding that we use is for operators that have a support on very few spins, like 1, 2, 3, 4, maybe 5, not much more. And this is related to a set of what can be, let's say, of what operators we can estimate efficiently using Monte Carlo, Markov chain Monte Carlo sampling. And so you see that this local operator essentially is telling you that it has 20 acting ons. This essentially means that it's a sum of many terms, and inside of it there are 20 terms. And then if I want to also build the the interacting term, like the sigma z term, what I can do is simply sum over all the nearest neighbor terms. So sigma z acting on the ith side times sigma z acting on the ith plus 1 modulo n. So this will have periodic boundary conditions. And if you see here now, this is saying that it's acting on 40 objects. That's because in this sum now I have put 40 terms. I have 20 local terms acting on one single site, and then I have 20 terms acting on nearest neighbors. And again, from the way that those are implemented deep down, the more terms in this sum, the more expensive evaluating this operator will be. So if you can rewrite your operator to have fewer terms, then this is always welcome. Now, you can also inspect essentially how we store those operators. And the underlying idea is that we keep every term you've added. So we have essentially 20 2x2 matrices that we are storing. So if you want the 20 sigma x matrices acting on the first 20 sites, and then we have 20 4x4 matrices, which are the sigma z terms. This also means that we can represent efficiently. This is not really a sparse encoding, because in a sparse matrix, you still have to encode like all the rows of your operators. So essentially, once you get to 64 spins, you cannot encode this as a sparse matrix anymore, because you cannot write down more than 2 to the power 64 let's say with standard packages. Instead, in this approach, we can write down operators on even thousands of spins, as long as the local terms don't act on more than 5 or 6 sites. And now, what is very useful to benchmark our implementations, even if it's not really part of the variational Monte Carlo procedure, is to convert those matrices to like some sparse format or to dense formats, in particular to sparse, so that we can use SciPy to extract, for example, the exact ground state energy. So in this line, essentially, I converted my operator to a sparse matrix, but then you can use to do whatever you want. And I then use it to diagonalize it using some standard routines, and I extract the ground state energy of this model, which in this case is minus 25.49, whatever. So the first thing I will try to implement is this mean field ansatz. I would like to show you. This is super simple. I will not show the code to really implement the neural network. Those are already built into NetKet. But the idea is that if you want, we have this product of some local contribution. And then, since we are in log space, we will actually be encoding the sum of those log phi, if you want. So leaving aside, for lack of time, exactly how we define the model, I simply take it from within NetKet, so the mean field model. Then what I do is I take some sampler. Essentially, we have several samplers, if you want. Essentially, the idea is that we have if you want, we have the exact sampler that Antoine mentioned this morning, this one. And then we have a bunch of other samplers using Metropolis, Markov chain Metropolis hastings. And the idea of Metropolis local is that every time, at every step, we propose a local flip. So I have my string of configuration. I select a random spin. I flip it. And then I check if the Born amplitude, so if the square of the wave function for this configuration is larger than the previous one. And since doing one, let's say, evaluating the network one at a time, one bit string at a time is somewhat wasteful of resources, we want to run many chains in parallel. In this case, I will do 16, for example. And we can also change the number of sweeps. So if you want the amount of subsampling that we do, the amount of subsampling that we do on the system. So in this case, I will try to use 20. Meaning that I will run my Markov chain algorithm 20 times for every step. I will subsample my configurations by a factor of 20. So those two objects, if you want, now I have those two objects, so the sampler and the mean field model, and my variational model, and I need to put them together in some way. So I need to find a way to, for example, initialize the model and generate the starting parameters. I need to set up my sampler. There's a lot of bookkeeping that, I mean, it's some people like and some people want to get into it, but many people don't want to. So the idea is that we have created these objects that we call variational states. MC state stands for Monte Carlo state. And the variational state essentially is some sort of black box, or not really black, but let's say gray box, that you can construct by passing it a Monte Carlo sampler and a mean field, a neural network architecture, and it takes care of everything for you. So then you can only query expectation values. You can get the quantum geometric tensor, or you can take gradients of expectation values, and so on. So you can use it somewhat as a cat for you, but internally it's doing some Monte Carlo sampling to compute expectation values and everything else. So this is the fundamental block that we try to present to users, in a sense. You can look inside of it, and you can define new algorithms. You can define new samplers, but the idea is that as this is the fundamental building block, it's an easy object to use to implement higher level algorithms. So for example, the dynamics or the ground state optimization or other things. And if you want, if we investigate this object, it will tell you a few things. For example, it will tell you what is the Hilbert space it's defined upon. He inherits this from the Metropolis sampler, which of course has taken as input the Hilbert space that we are sampling. It tells you what sampler we are using. It tells you how many samples we have. Okay, 80,000 is a lot. So I will actually tune it down to 1,000. This will actually complain that 1,000 is not a multiple of the 16 chain, so it's changing it to 1,008. And it's telling us how many parameters our neural network architecture has. And as I choose a mean field ansatz with that is translational invariant, I only have one parameter, so it's quite trivial in a sense. I will skip that for a moment. And so if we use this object, we can, for example, compute expectation values. So I do this vstate, variational state, dot expect. Expect will compute the expectation value of an operator, and I will pass the Hamiltonian. And this tells us minus 19.91. So that's the energy of this state. Let's say for these initial parameters, we can also investigate the parameters by doing the state.parameters. This case is minus 0.001. Okay, and when I compute an expectation values, we also will return you the statistical error in this estimate, which is very important to know if you can trust this value or not, and up to what decimal digit. It will tell you the variance of this quantity, which is useful because essentially when you have a zero variance, you know that you are either stuck on some eigenstate of the Hamiltonian or that there are some sampling problems. And finally, this gives you what we call the hat, which is a convergence indicator. This is very important if you try to run this kind of calculation. Essentially, this number, if it's very close to 1, it tells you, well, your Monte Carlo Markov chain are somewhat converged. Instead, if they start to deviate, so they are around 1.05, 1.06, it means your Markov chain Monte Carlo sampling is off. And so, for example, you might find energies below the ground state. That's because you're not being ergodic, you're not sampling the whole Hilbert space, and so you can find completely unphysical results. Because I want to stress it, neural network quantum states and variational Monte Carlo methods in general, they are effective and you can trust them only as long as you can trust the sampling. If the sampling is off, you cannot trust anything they tell you. So you should always be careful in checking that this R hat or whatever other convergence indicators tell you that all is good. Actually, this object is hiding more information. So you can, for example, see that we also store inside of it some correlation, some tau core. So it's the correlation time along the Markov chain. So in this case, it's very small. It's essentially 0, which means that, that's good. It means that the samples are essentially uncorrelated. But sometimes it can happen that you have a huge correlation time. And in that case, you should be wary of, and you should not trust all the quantities that you are computing. Yes. In particular, yes, you can see here all the quantities we were discussing here. So the mean, the variance, the standard error that we call sigma, the correlation times, and the R hat. And you can, so there is, if you go online, you will find a very large discussion about what this Gell-Mann-Rubin diagnostic tells you and how to read it, in a sense. Another, of course, to minimize the energy, we don't only need the let's say the energy itself, but we also need the gradient. So that's the idea behind this command, which is expect and grad, to which you pass the Hamiltonian, and so it returns a tuple. So the first object is the energy, as before. You can see that it's exactly identical to before. So in this case, that's before we did not resample. Essentially, this object caches the samples unless you change the parameters or you explicitly tell him to perform the sampling again. And the second object is the gradient of the energy. So this is some dictionary that has the same structure of your parameters so that you can sum every set of parameters with their set of gradients. And with this, essentially, you have everything you need to write down an optimization loop for the energy, right? So you construct a variational state. Then you can loop over a certain number of steps. You can compute the gradient. We can store in some list the energy. And then we can update the parameters. So what this JAX.3 map does essentially is that it looks at every set of parameters, because the parameters are conceptually a vector, but in practice they are stored as, if you want, a list of blocks of parameters. Because I have, for example, in the restricted Boltzmann machine, I would have the W matrix, the biases, the visible and the hidden bias, etc. So this tree map essentially applies this function, which is simply, if you want, that's the meaning of what I want to do. I want to take my parameters and subtract the gradient times 0.05. And it applies this function to every corresponding set of parameters between the list of parameters and the list of gradients. And then we update I don't know why this is cut, but we update the parameters of the variational state with those new parameters. And if we run this, we can then plot this list of energies that I computed, and it's broken. Yes. Why is this? I think it's because my yes. So, and if I plot this, you can see that we converge down to some energy. So this is somewhat annoying. The idea behind NetKet is also to try to make it somewhat easier to do this kind of calculation and hide all this boilerplate if you want to from you. So you can always write your optimization loop yourself, but essentially we provide some much simpler, we call it driver interface, where this is done for you. Essentially, you can, we can reset the parameter for a moment. You can take one of the optimizers that we provide. We also have some packages. You can also use some packages for the optimizers. And then you can construct this object, the netket.driver.variational Monte Carlo driver, to which you simply specify the Hamiltonian, the optimizer, and the variational state. And then you can simply say, just run the algorithm for 300 steps, and store the output somewhere. So we have those loggers as well that are used to store all the informations. And if you do this, essentially the idea is that this also saves to file everything you need, and I mean, it's a somewhat nicer interface to run this kind of calculations. And if we look at the ground, if you look here, for example, by minimizing the energy for this very trivial mean field ansatz on the 20 sides with a single parameters, we are already able to get an energy of -25 against the exact value, which would be -25.5. So, of course, we want to improve this result. So the next simplest ansatz that we can take is, for example, a Jastrow ansatz. I will not get into the details of why we use these structures. It's very well described in the original paper by Jastrow, actually. Let me also cut these. So. And I can take the Jastrow ansatz defined inside of NetKet, netket.models.jastrow, and then I can create a new variational state using this model. So I will specify the sampler, the Jastrow ansatz, and then a certain number of samples. And you can see here already that the ground state energy, okay, it's fluctuating somewhat, but okay, it's not. Okay, let's remove this. And in this case, you can easily see that, okay, the ground state energy is not really improving too much with respect to what we were using before. Unfortunately, that's also because we are maybe using a too large learning rate. So that's where optimizing this kind of neural network structure becomes an art. Okay, that's still not good. Let me go to the actual one for the last thing to flash, because I think it's already 4 p.m. So what if we want to use a neural network quantum state? So essentially the restricted Boltzmann machine that was introduced this morning. Again, you can either take the one that we define inside of NetKet, so this restricted Boltzmann machine, and you can specify a certain value of alpha, for example. Or you can also define this neural network yourself. And the idea here, this is using a neural network package called Flux. If you are interested in this, I would invite you to look at the documentation of Flux itself. But the idea is that you define this method, like call, which evaluates your neural network ansatz, and we use a dense layer, which is essentially this matrix vector multiplication. We multiply, this encodes this W matrix that multiplies our bit strings of the inputs. Then we use a ReLU activation function, and then if we want to add another layer, we add another dense layer with a certain number of outputs. We apply it again to the output, we use another ReLU layer, and then we can sum over the output. The message here is not really to go in the details, but if you want is to show that it's extremely easy to write a neural network architecture. Literally takes 5 minutes, and you can combine over, and you can try to add more layers, or you can try to add some symmetries by hand inside of those structures. Okay, and now I forgot to import all the relevant models, so it's so this will not work, but let me try to do this. And now if we look at the structure of the parameters, for example, you remember that before we had a single parameter, but now we have a restricted Boltzmann machine with alpha equal to 2. So if you want, my parameters is this dictionary or this list of many arrays. So we have the bias, which is this vector of 20 elements. We have the kernel, which is this huge matrix, if you want. And we have other terms. So in a sense, If we just look at the structure of all objects, if you want, the bias is this vector with 40 elements, the kernel is a 20 by 40 matrix, and the visible bias is a vector of 20 elements. And then again, once again, we can try to run this calculation. We can use variational Monte Carlo to find the solution. You will see that now with a restricted Boltzmann machine, it's slightly slower. Still, it's running on my laptop. Those are 20 spins. And it will scale quadratically if we increase the system size. You see that it's struggling somewhat to find the ground state energy. This is probably we need to do some more steps. For example, you see that the learning rate, so the steps I'm taking are 10 to the minus 3. They are very small. So what I could try to do is to increase the learning rate to 0.01. And in this case, you see, yes, finally it's starting to converge. The ground state energy is minus 25.49. Okay, we're not exactly converging yet, but we are not too far. So 46, of course, what you should actually do is to try to increase somewhat, to try to look at the fluctuations towards the end of your optimization. And let me, and if I plot the energy, if you want, you will see some behavior like that. So, and now if you, for example, want to, I don't know, see if you can improve the result by increasing the size of a neural network, again, with this kind of neural network, it's very easy to increase, I don't know, the hidden unit density, so we can put alpha equal to 4. In this case, we will also need, for example, to increase the number of samples to something more like 4,000. And in this case, we can try to rerun the calculation. And hopefully, we should find some better results. And essentially, that's the bottom line, if you want. What happens most of the time, we stare at our screens where those progress bars go on, and we try to find better and better approximations for the ground states. I will not bore you to death with trying to find the ground state energy for this model. With an RBM, it's possible, and it's not terribly hard to find a very good approximation. I mean, as you've seen, Giuseppe has found errors around 10 to the minus 4, 10 to the minus 5. The last thing I want to stress is that once you find a quite decent approximation of your ground state energy, what you will want to do is to take this variational state and start to compute some over properties. So not only the energy that we were looking at now, but for example, you will want to look at, I don't know, the magnetization along some axis. So we can write down the magnetization along the z-axis, which will be the sum of all the sigma z high for E in range n divided by n, and then we can compute those quantities. And especially since the expensive part of those algorithms is the optimization that we do. If you want, what we often do is that we find a solution by keeping, I don't know, 4,000 samples along the optimization, and then when we are done, we will put, we will specify that we want now 40,000 samples, and we will compute the expectation values with 40,000 samples, such that if you note, if you remark the error bar on this, the statistical error bar on this quantity is considerably smaller. So if you want, we do the optimization with fewer samples because otherwise it's too expensive, and then at the end we increase enormously the number of samples. So I think I'm done now. I think it's well past time. If you are interested in those things, I would really invite you to go on our website, NetKet. As I said before, that we have an extensive documentation. We have a few tutorials, like the first one on the Ising model. It's exactly what you saw today. You can run it on the internet yourself very easily. There's a few more advanced tutorials. And we have somewhat, let's say, extensive documentation where we try to keep everything very well documented so you can play with it. And in particular, while it's not very well documented, we also have some logic to study the, it's not here, I think. Yes, the dynamics of the TDVP, so essentially the dynamics of quantum systems. Unfortunately, it's not on the website yet, but you can check out the paper. And we have some tutorials on the paper as well. Fortunately, it's a bit scattered. One day we will put it all together. And with that, I will conclude. And I don't know if there are some last questions. Thank you.